Okay, so I think we're good to get started. The last assignment is open. When you click on it, you'll see that it has a lot of questions, but a lot of those are multiple choice questions. You know, part A is find the magnitude of something, and then part B is a multiple choice, find the direction. So it's sort of an artificially inflated number of questions. Hopefully all those multiple choices will go fast. If you have questions about the assignment, of course, as usual, get in touch or reach out to the Help Center. And most of the stuff I do in class will help you get through that assignment. And it's not a bad summary for the material. Okay, before we get started, does anybody have any questions? Okay, so here's something, I put this up, something for you to ponder as we go through. And then we'll circle back around to this question a little bit later on, and we'll see if anybody has an answer for it. It's a good question. So we'll come back around and we'll answer this. Certainly not today, but maybe Monday or Wednesday, but we will come back to it. Be interesting if you can come up with the answer before we talk about it in class. Okay, so did I ask, does anybody have questions before we get started? Okay, we're good. So early in the course, we talked an awful lot about this. A charge in an electric field, that's made by some sort of source charge, will feel an electric force. We spent loads of time on that. We know that electric forces are charge times electric fields. They're vectors. The direction of the force depends on the sign of the charge, all that stuff. So we did tons of that. So now we're coming around to magnetic fields. And I'm going to switch over to the computer because I have a video. And what happens is that it turns out if we put a charge in a magnetic field, that will feel a magnetic force. So just like charges feel electric forces, they can also feel magnetic forces. This is a video about our current lab. So Monday's group have done this, and I think Thursday's group does it tomorrow. And this is a little recap of what you'll be doing tomorrow. So he just sanded off the ends of the copper wire. Then he's got a stand, power supply, making a little circuit, puts the loop in, turn on the current, it'll flow through the wire. If we bring the magnet before we connect the circuit, we have nothing. We connect the circuit and it starts to spin. Okay, so the magnetic field makes the force. The size of the field seems to influence the motion. The direction of the field also influences the motion. Okay, so this is not news to Monday's lab, and it's something that Thursday's lab will look at tomorrow. So this is pretty cool. These little motors are so neat. It's probably the best lab I think we do in the whole physics department. It's just cool. So we definitely know that a moving charge, and in that little video, we know we have moving charge because moving charge is current, right? So moving charge, if we put it in a magnetic field, you can make that by a permanent magnet or another moving charge, it's going to feel a magnetic force. So there's some observation. So what do we know about this force? So experimental results. So that's what happened, is people noticed this effect, and they experimented with it, and the primary findings were, first of all, the size of the force, the magnitude of the force, it's proportional to the size of the charge, so it depends on how much charge. It's proportional to how fast the charge is moving, and it's proportional to the size of the field. So the force depends on all of those things. Change any of them and you change the force. A neat observation. Some of you will probably see this in the lab, right? When you do the lab, it very much matters how you put that coil near the magnet. That's really important. People who couldn't get their motor running, probably that's the first thing that the lab crew had you check was the orientation. So it turns out if the direction of the velocity and the direction of the speed are parallel, direction of the field, those two things are parallel, the magnetic force is equal to 0. Okay, that's kind of interesting. If they're perpendicular, so V perpendicular to the magnetic field, your magnetic force is a maximum. That tells us that the magnetic force depends on the angle between the velocity and the magnetic field. Doesn't exactly say how, but it definitely does depend on that angle. What else do we know? If we put in a negative charge instead of a positive, we get the opposite direction for the magnetic force. Okay, so if a positive charge has a force to the right, a negative charge in the same situation would have a force to the left. So we'll say FB is opposite if the charge is negative. We can sum up all of this in a single equation. The result is that the magnetic force is the charge, and we include the sign of the charge here, it's not the absolute value, times V cross B. So earlier in the semester we did scalar products. We said it was a way of multiplying two vectors to get a scalar for your answer. This is called a cross product or a vector product. This is a way of multiplying two vectors to get a vector for your answer. I figure everybody has seen this. I've got some practice up on Brightspace if you haven't seen it or if you're a bit rusty. And we'll do a little bit in class as well for a review, or you can come talk to me if you want to go through it. So this is called the vector product or the cross product. And that makes sense because magnetic force is a vector. We expect it to have direction at the end. So when we're finding these magnetic forces, we can always do the math version. We can put in our values, take the cross product, and find our magnetic field. Or we can do a magnitude with right-hand rule. So if we want to find it, we can find the magnitude of our magnetic force using the magnitude of the charge times the speed times V times sine of theta. Got to be super careful with theta. That's the angle between the velocity vector and the magnetic field vector. And the right-hand rule applies to positive charges. To use our right-hand rule, if you talk to physicists about a coordinate system or vectors, you'll see most of them do this. Okay, we kind of all do it. And sometimes you won't even notice, but everybody's doing it. So when you're doing a cross product, you've got your first vector, that's your thumb, crossed with your second vector, that's your finger, gives you your answer, that's the middle finger. So V cross B equals F. That works for every single cross product. Okay, so that's what we're going to do when we use the right-hand rule. Lots of times I get people ask, I learned the left-hand rule in high school, can I still do it? My answer to that is you're grown-ups, I can't make you do anything. I would recommend you switch to a right-hand rule. It's what all of the books you'll see from now on supports. High school does a left-hand version, comes from thinking about moving electrons versus moving positive charges. But from now on, you're going to see right-hand rules, so you may as well get used to it. Okay, last thing before we move on is let's just think about this for a second, because this is kind of crazy. Okay, let's imagine, so B is a magnetic field, just like we have gravitational fields and we have electric fields. What if force due to gravity was like the force due to a magnetic field? Kind of what would that mean? First thing it would mean is if you stood still, gravity would turn off, right? So weight wouldn't exist if you stood still. That would be strange, right? So that would be a weird planet. So you would just kind of start to float up. You would feel no force due to the Earth if you stood still. Alternatively, you could move, but you could move up and down. Okay, still no gravity. Okay, so you could move up and down as much as you wanted to if a gravitational force was like a magnetic force. But the moment you stepped sideways, you would fall on your face. Okay, that's very strange. So magnetic forces are very weird forces, right? Electric forces and gravitational forces, they align with the fields and they sort of make sense, right? The way the field pushes is the way you feel the force. That doesn't happen with magnetic fields. So this is very weird. So I just kind of like to think that out. Okay, so let's go to some practice for this stuff. So, example number 1. Let's start straightforward. Let's say I have a positive charge. It's moving to the right and the magnetic field points up. what would we get for the magnetic force? And just to come to notation, we're used to doing up, down, left, and right. We're comfortable with that. When we have a three-dimensional coordinate system, we have a z-axis. So x, y, and z also follow this. So this is x, this is y, z is out of the page, right? So positive x to the right, positive y up, positive z points towards you. We want to draw a vector that points out of the page. We put a little circle with a dot in it. If we want to point it into the page, we put an x in it.
It'll be a circle with a dot.
Pardon?
It'll be a circle with a dot.
For this answer?
Yep.
Yeah. So this notation comes from thinking about an arrow. Right, so if it's coming towards you, you're seeing the tip of the arrow. That's the dot. If it's going away from you, you see the flights on the back. So that's why it's an X. So that's what that notation is from. Okay, coming back to here. So there's your V, there's your B. So the first answer we got was out of the page. So at this point, I should see everybody's right hand out, trying to get that direction. Seeing if you agree or disagree. So who agrees with out of the page? Okay, sometimes hard to tell because the hands are up anyway. So you put your V in this direction, your B comes up, your force comes right out towards you. So that is absolutely correct. So our magnetic force is out of the page. You can also do it the math way. So our magnetic force is Q. Our charge is going to be positive times V cross B. V is to the right, that's the plus X direction or plus I hat. And it's crossed with B, that's up, so that's the J hat direction. So the direction of our force is going to be positive I cross J. People probably have lots of different ways they remember I cross J and J cross K. I still remember what my first year physics class showed me, is you make a triangle with I, J, and K. You point them to each other going around the circle. If you go the right way around the circle, you get positive answers. If you go the wrong way, you get negative answers. So I cross J is going the right way, gives us plus K. That's the way I remember it. You may have your own tool, which is just fine. Plus K. Okay, so there's example 1. Questions? Okay. All right, what about example 2?
Into the page.
Okay. Very quick answer, be into the page. Agreement? So this one is a negative charge. We've got the same situation. So we do our right-hand rule, QV, B, or V cross B gives us force. We remember that the right-hand rule tells us the force on a positive charge. This is a negative, so we got to rotate our answer by 180 degrees. So our right-hand rule says out of the page, but it's negative, so it has to be into the page. And then if you want to do the math, it supports that. We've got minus I cross J equals minus K. Good to hear? Okay, we'll only do a couple more of these. And then I've got a few on the problem set next week for extra practice. So for our next two, I've got V going into the page, B is to the left, and the charge is negative.
Up.
Okay, first answer I heard was up. Does anybody agree? Some head shaking there. Anybody have a different answer?
I would say that the result is going to go down.
Okay, got some down. Anybody agree with down? Getting some nods, thumbs up. Okay, so let's go through it. V is into the page, that's our thumb, so your thumb's got to be going into the screen. Then our B is going this way. Sometimes you might just twist your paper if you're having trouble doing it, right? It's the easier way to do it, right? V is into the page, B is like this, then you extend your finger, you come back around. That shows going up, so V cross B goes up, but it's a negative charge, so we got to rotate it by 180. So that negative can really get you.
Can you do the hand thing one more time?
Oh yeah, for sure. Okay, so V is into the page, thumb is into the page, and then this finger, we got to rotate our wrist so it matches B. I'm coming around like this. Okay, you're getting closer. Then you extend the middle finger, and that's pointing towards the ceiling.
Okay. And then it's opposite because it's negative.
And then it's opposite because it's negative.
Thank you.
Okay. Practice is definitely key here. I can always tell when people get to the magnetic field question on the exam, because everybody's kind of doing this. You can see it right off the bat. If you wanted to do it with the math, we've got negative. V is into the page, that's minus k. Then we're crossing it with B, that's in the minus I. So minus, minus, and minus, that's gonna give us a minus. K cross I. K cross I, that gives us plus J, but we got a negative here, minus J. So if you're looking to confirm your answers, this is not a bad way to do it, especially if you're a little bit unsure about that right-hand rule. Okay, what about example 4? Some shrugs, some funny faces.
I'm saying
First
zero.
answer I got was a 0. Anybody agree with 0? Yeah, okay. So those are parallel. We know that the force is going to be 0. Math-wise, we've got plus. V is up, that's J hat cross J hat. Something cross itself is equal to 0. If you were trying to do your right-hand rule, this would have to go up, this would have to go up. You can't do that, right? So the force is 0. Okay, next one. So let's get one at an angle. So our last example, so V is up, it's got an angle of 26 degrees, up and to the right. B is straight up, we want to find the magnetic force. Q is 1 microcoulomb, V is 450 meters per second, and we know our V there. Two ways to do it, we can do the cross product, or we can do magnitude and right-hand rule. Neither way is better than the other, but magnitude and right-hand rule would be faster. If you wanted to do cross product, you'd have to write this one in components and then do it all the steps for your cross product. Certainly it's doable. If you're kind of more math-minded, you might choose to do it that way. But let's go through the right-hand rule way. So the magnitude of the force, FB, is the magnitude of the charge times the speed times the magnetic field times the sine of the angle between V and B. Maybe you remember back when we did the flux chapter, flux was E dot A. You had to be really careful about the angle. That's true here as well. You got to be careful with the angle. If I gave you this angle down here, that wouldn't be the right angle to use because our V is this way, B is this way, the correct angle is 26. Just make sure you're keeping an eye on that angle as you're doing the problems. So Q is 1 times 10 to the minus 6 coulombs. V is 450 meters per second. B is 0.750 Teslas multiplied by sine of 26 degrees. The size of our magnetic force is 1.48 times 10 to the minus 4 newtons. We need to get the direction. We can do our right-hand rule here. Our thumb goes with V, our finger goes with B, and then our middle finger is force, which is coming right out of the page. So the direction is out of the page, K direction or K direction, whichever way you'd rather write it. So FB as a vector is this K hat. Some people use the K notation, some people write out of the page.
So just then when you were lining up your thumb with V,
Yeah.
you put it like in the direction of like the X piece of V? You know
Well,
I
what
mean?
I actually did was I lined it up with the V right there.
Okay.
So this finger was B, and this one's coming off at an angle.
Right, you can make that angle. with
Yeah.
your fingers.
I can do that angle, so I thought that was a legitimate thing to do. It's also acceptable to think about the fact, and this is kind of going a little bit deeper, but it's still okay. Our velocity has two components. It's got a bit that's perpendicular to the field, and it's got a bit that's parallel to the field. So this is our Vy, this is our Vx. This part doesn't do anything. So yeah, doing your right-hand rule, it would be okay just to line up with the x component. That's absolutely fine. So the x component cross with V gives the force. You still get the same answer. Okay, questions? Is that part okay? So, let's say we've got a negative charge flying into a magnetic field. The direction of the magnetic field is into the page. That's what the X's show us. What is this charge going to do? Is it going to veer up, go straight through, or veer down? What do we think? Okay, so the people who are doing this are thinking about the direction of the force. That's good.
Veer down.
Okay, answer is veer down. Anybody? Some nods. Disagreement? Tricky stuff, right? So, thinking about the force, V goes this way, B is into the page. So our thumb's this way, B is into the page. Middle finger sticks up. The right hand rule is for a positive charge. This is a negative charge, so the force can't be up, it has to point down. If the magnetic force is down, then it's going to have a force that points down while it's drifting to the right. It's going to deflect downwards. So path 3 is the answer. I'm pretty sure I got questions like this on the assignment, so that might help with that. That might even be the first question. I had to look at it yesterday. Yeah, you may end up with cramped hands. Okay, so the next bit is let's sort of talk about this kind of thing a little bit more. So what if we have the situation where the force, velocity, and magnetic field are all perpendicular? So everything is perpendicular. When we do a cross product, so to find our magnetic force, we do FB equals QV cross B. You might know from the math, or you might have figured out from the right-hand rule, that no matter what you do with your V and your B, your force always sticks straight out of your palm. Your force is always perpendicular to both of them. Okay, so that's one conclusion we certainly have. So FB is perpendicular to the velocity. FB is perpendicular to the magnetic field. And since V is perpendicular to B, because it says they're all perpendicular, that tells us that the angle between the two vectors is equal to 90 degrees. This part here, that the force is perpendicular to the velocity, that might be ringing a bell from Physics 1050 or 1020. Okay, what happens when we have that? When we write down our magnitude of our magnetic force, we would get QVB times sine of theta, but theta is 90 degrees, so that would be Q times V. Oh. Q times V times B. Sine of 90 is equal to 1. Okay, so now let's think about what if we have this positively charged particle in this magnetic field that's pointing into the page, and our particle is moving straight up. Let's find the direction of the force. So V is up, B is into the page, our force is to the left in this case. So the magnetic force here is going to point into the left. There is our FB. Okay, so it's moving up. It has a force to the left. What's going to happen to the motion? It's going to move to the up and left, right? It's going to move partly up and partly left. So it's going to come along. Eventually it's going to get to right here, moving up and left, kind of going this way. There's our new velocity. If we want to get our force, V cross B points in this way. There's our force this time, FB. A little time later, it might be up here. Velocity is coming over this way. Right-hand rule shows our forces down this way. FB. Just ringing some bells now.
So if you have a big enough field, you could get that, thing going in a circle.
There we go. That's what I was hoping to hear. This is circular motion, right? Anytime you have your force perpendicular to your velocity, that's the same as acceleration perpendicular to velocity. This is circular motion, and that's what happens in these problems. The charged particle will move with circular motion, and when we have charged particles in a magnetic field, we call it cyclotron motion. So we get circular motion. And that's called cyclotron motion. So these fields, electric and magnetic fields, this is how we control the motion of teeny tiny particles. You've probably heard of cyclotrons. Triumph out in BC is probably the biggest Canadian one. Okay, that's where they do stuff like this, right? They do all this kind of analysis. They usually hire a bunch of summer students. Not a bad way to spend summer. So let's look at a picture I nabbed from out of your textbook. So I'm pretty sure that's this textbook. So in this picture, these two things right here, they're big copper coils, bigger version of the coils you had in the motor lab yesterday. They're running current through it, and those currents make a magnetic field. We're going to come around to learning about that. So we've got two magnetic fields on either side of this glass chamber. It's about yay big, and it's full of gas. Okay, so this thing here is a glass chamber full of gas. On one end, we have an electron gun. Okay, so that just shoots out electrons from the filament, gives them a certain speed. Those electrons come into this area where there's a magnetic field. It feels the force perpendicular to the velocity, and it moves in a circle. What we're seeing here are the electrons are going in a circle because of the magnetic force. They're colliding with the gas in the chamber. When they do those collisions, it gives off energy in the form of light. That's why you can see the path. So they do lots of experiments of stuff like this. You can measure the radius of that path. That gives you information about the charge and the mass of the particles. It's a way to learn about kind of fundamental particles. Pretty cool stuff. Okay, so let's apply an analysis to this motion, to this circular motion, just like we do in 1050 or 1020, and see what we can figure out from that. So we can apply Newton's second law. Sum of the forces is mass times acceleration. These particles are so teeny tiny that we pretty much always neglect gravity. The only time you'd have to include gravity on a test question is if I say the particle has significant mass, the particle is very heavy, things like that, that's when you know you have to include it. Otherwise, if we've got these little protons and electrons, we know we can neglect gravity. So the only force we've got here is the magnetic force. That's equal to mass times acceleration. Our magnetic force is QVB sine theta. Acceleration, when we go in a circle, is mv squared over r. We've already established that our theta is 90 degrees because everything is perpendicular. So that little bit is equal to 1. I've got a v squared on this side and a v on this side, so I can divide both sides by v. And that leads to the result that the radius of the path of those charged particles is the mass times the velocity divided by the charge times the magnetic field. That's the radius of path of moving charge Q in magnetic field P. Okay, questions? Okay, still good, huh? So this talks about what if the velocity and the magnetic field are perpendicular. That might take us to the next question. What if the velocity has a component that's perpendicular and a component that's parallel? That's a good question, right? So what if B has component parallel to the magnetic field? So I tried to look up a bunch of demonstrations online. They're not very useful, so I came up with a ball on a string. So if the force, if the velocity is perpendicular to the magnetic field, we already know we're going to get circular motion. We're going to get this, so when it's completely parallel. If we have a component of velocity that points up, that bit of velocity won't make any magnetic force. So let's say our magnetic field is into the ground, points down. Our velocity is this way, the force is perpendicular, so it goes in a circle. If I have a component of velocity that points up, there's no force, so that velocity won't change, so it'll just move up. Right? So we'll do this. So we'll start down low, keep going in a circle as it moves up. It forms a helical pattern, so it will move in a helix, so that's kind of neat. So the perpendicular bit of the velocity, that gives us our circular motion. The parallel bit of the velocity, we say that it just drifts in that direction. And then together, that makes a helix. Yeah.
Can you do that again? I didn't get that.
Okay, so let's say we have a magnetic field that points down into the ground. If this has a velocity that points, say, towards you, then the magnetic force is going to make it go in a circle. Okay, so that's what the perpendicular velocity does, makes it go in a circle. If I had this ball and I just had it moving upwards, the magnetic field would be parallel to the velocity. Nothing would happen to that velocity. So the two bits do two things. The perpendicular means a circle, the velocity means it goes up, and that's what it looks like when we have a circle going up. It looks like a helix. So my favorite illustration of this effect would be the Northern Lights. I've only ever seen them kind of once in my life. I was living with my parents in St. Mary's Bay, and it was like super dark, and there had been a solar flare earlier. Has anybody seen it? Yeah, some. Is it kind of as amazing as I think it is?
Yeah.
It's definitely on my list, right? Is go north in Canada in the wintertime and see these northern lights. So kind of what happens with the northern lights is a big amount of charge gets blown off the surface of the sun. So you get these sunspots and sun explosions, and charge just blows right off. The charge from the sun kind of blows off in whatever direction it blows off. So sun comes towards the earth. The charge gets close to the earth. It comes in an area with a magnetic field. And then that demonstration happens, right? Part of the velocity is perpendicular, makes it go in a circle. Part of the velocity is a drift, makes it follow, just go straight. So those charged particles are going to move along the magnetic field lines as they go in circles. When the charges get into the atmosphere, they're going to collide with the molecules in the atmosphere, just like the electrons in that little chamber of gas. As they collide, they give off energy, and the energy comes off as light. So that's this. I kind of read some places online where people say that they can hear the northern lights. I don't know if that's true. To me, those northern lights, they happen pretty far up in the atmosphere. It's kind of hard for me to buy that the sound would travel to a person standing on the bottom.
Maybe if they had some sort of hearing aid, they could pick it up.
Yeah, maybe. There'd have to be a lot of attenuation though, right? Like, it happens pretty high up in the air. I don't know, right? One of these things I'd like to see for myself. It also sort of makes me think about, you know, people certainly have understood magnetic fields for a long time because you could see it and touch it. But this seeing of the magnetic field effects in the atmosphere as the northern lights, that's kind of a new understanding in humanity. So what did people used to think about that? Like, that's sort of interesting to think about, right? Just all of a sudden the sky is glowing, and, you know, was it a bad omen? Was it a good omen? Anyway, that's not strictly physics, but it's still interesting.
I know some native cultures thought of it as spirits walking, if I remember.
Yeah, spirit walk. Yeah, I could totally see that. Yeah, I would like to learn more about that kind of philosophy. So, let's do a question with some numbers. So let's grab an electron, let's shoot it into this field with a speed of 1.7 or 1.5 times 10 to the 7 meters per second. And what happens to the electron? So let's write down some things that we know. The speed is 1.5 times 10 to the 7 meters per second. The charge is, it's an electron, so it's negative the fundamental charge. Mass of an electron is something I tend to remember, but I would give you guys on a test if you needed to know. and the strength of the magnetic field is 3.14 Teslas. So we're taking the electron, we're shooting it into the field. Let's say it comes in right here, and it's coming in, moving to the right. First thing we need to establish what's going to be the direction of the force on that charged particle. I kind of gave that away earlier with the question when I said which path would it follow. So the velocity is to the right, the magnetic field is into the page, makes the magnetic force point up, but it's an electron, so it's negative, so we got to flip it and it moves down. So there's our magnetic force. We know it's going to move in a circle because we know this produces circular motion, and we know that that circle is going to be deflected downwards. So the path is going to look something like that. So we're going to get circular motion deflected downwards. So let's apply our Newton's second law analysis here and see what we can learn. The sum of the forces equals mass times acceleration. The force is going to be the magnetic force. Magnetic force is QVB sine theta. In a circle, our A is V squared over R. I know we did this just a minute ago, but it's kind of worth starting from scratch every time. Theta is 90 degrees, so sine theta is equal to 1. We're trying to find the magnitude of the magnetic force, and we're going to use the magnitude of our charge here. So the magnitude of our charge is the size of the fundamental charge, so E times V times B equals M times V squared over R. One of our V's will divide out. The radius is equal to M times V over E times B. Put in our numbers. And the radius of that path would be 2.72 times 10 to the minus 5 meters. That's about 27 microns. That's pretty small, a little bit thicker than a human hair. That feels really small to us, but it's pretty big for an electron, right? Because electrons are tiny. So are we good to here? So this is just plug and chug from the previous.
So the question asked like what happens to it, and then we found radius. So the way to answer a question like this would be like the electron moves in a circle with radius this.
Yeah.
That's what we're looking for.
If this were a test question, it would be more well defined. In
Right.
class, I can be vague because who knows what I'm going to want to talk about at the time. Yeah.
For sure.
Yeah. Okay. But on a test, I would try very much to clarify. Otherwise, you're trying to guess what I want. Okay, so we know that this magnetic field is going to make it to go in a circle. A lot of times when we're doing experiments on fundamental particles, we don't want stuff going in a circle. We want it to go straight. So how do we make it go straight? It's kind of a good question. So let's look at that part next. So if we want the charge to go straight through, let's think about what it means for the charge to go straight through. So it's got a velocity, say, to the right. We want it to continue going to the right with that velocity. If we want it to not deflect up or down, you know, the magnetic force makes it swing down. There's going to have to be a force that makes it go up, right? The only way to get it to go straight through means there has to be a net force of 0. So we have to understand that that's what we need is a net force of 0. So next we ask what sorts of things make forces on charges. Well, we have two things. Magnetic fields make forces. We just talked about those. And then we remember that electric fields also make forces. So if we want it to go straight through, we need a magnetic field and an electric field. And we need that electric field to be just so that the magnetic field force and the electric force cancel. Okay, so there's our goal here. That's what we have to do. And this question is asking that sort of straight out, but that's the thought that gets us to this process. So in our picture, we've got our electron, that's a negative charge. That's moving to the right with velocity v, and we want it to keep doing that, so we want it to go straight through. To go straight through means no deflection. To get no deflection, we need the net force, remembering that forces are vectors, we need that to be 0. We have already established that our magnetic force points down. So we can draw that on our picture if we wish. There's our magnetic force. So if the magnetic force points down, we want the net force to be 0. We've only got one option for the direction of the electric force, that has to point up, right? So therefore, Fe points up. So let's put our electric force on here. As soon as you get to that thought process that the electric force has to point up, and you know the charge is negative, that should be enough information to tell you the direction of the electric field, okay? So you might do that step first, you might not, but it is kind of important to know that you could do that, right? So we've got a negative charge, the force points up. That's enough to tell us that the electric field has to point down. But we're still going to go through the process and solve it. So let's do a Newton's second law approach. So we know that the net force is 0. And I'm going to be really careful about the vector business here, because I'd like to find my electric field as a vector by following the math. Then I'm going to confirm the direction of my answer with what I think it should be. So my two forces are my magnetic force plus my electric force equals 0. My magnetic force points down, so it's going to be in the negative j hat direction. The magnitude of that force was E times V times B. So EVB, that was the magnitude that we got from the previous slide, negative j hat because it points down. Plus my electric force. My electric force is the charge on the electron, I'll just do QE for the moment, times the electric field, which is a vector. For my next step, I'm going to put in that my charge on the electron is negative of the fundamental charge, so QE is minus E. Now what? I'm going to bring my electric field to one side and the magnetic stuff to the other side, so minus E times E equals plus E times V times B j hat. I've got E on both sides, so I can cancel those, divide through by the fundamental charge. And then I'll divide through by the minus as well to get E equals minus VB j hat. If I look at this answer, it shows me that my electric field points down. That confirms what I got from knowing that my electric force pointed up for a negative charge. And I see here that the magnitude of my electric field is equal to V times B. So this kind of a device, and if you do go work at Triumph for the summer, you'll see this all over the place too. This is called a velocity selector. So if we put this electric field with this magnetic field, particles that have this speed and this speed only go through. If we change the speed, they'll either deflect up or down. So changing the speed would change the deflection, and only the ones that get the sweet spot get to go right through. So this is a velocity selector. So it allows only charges with speed equal to E over B to go straight through. And then if you were thinking physically about where does that field come from, you would have something like a giant capacitor on either side there. So you would have one plate here. You would have one plate down here. We've shown and we've reasoned that the electric field has to point straight down. That means this upper plate must be positive and this lower plate would have to be negative. Okay, any questions? No. Yesterday I posted a new example. Why don't we get started on that? So last night I posted one slide on Brightspace and said we would do that either in today's class or tomorrow's class. We kind of have enough time, so let's get started on it. This one has a lot of words, but it's kind of a short question. I think we have time to get started. This question, I took this off an old exam, so this is kind of also to give you an idea of what an exam type question would look like. You'll also have stuff like this on the problem set next week. So we have positively charged ions are shot from a source. So this is emitting positive charges coming in this way. They're first passed through a velocity selector. So we've got our electric field down and our magnetic field into the page. We know the size of those fields. Part 1, draw the free body diagram on an ion passing straight through the velocity selector. So it says, think about a charge that's right here. What do the forces look like? So there's our positive charge. The velocity is this way. So if we want to think about the direction of the forces, let's do the electric force first. So we know electric force is equal to Q times E. Our charge is positive, our electric field points down, so the force is the same direction as the field, so the force also points down. Here's our FE. For our magnetic force, we kind of have two ways to recognize what that answer is. It's a velocity selector. It has to go straight through, so the magnetic force has to oppose it. It has to be up. But let's confirm it with the right-hand rule. The velocity is to the right, that's this way. The magnetic field is into the page, so our index finger goes in. The middle finger points towards the ceiling, so up indeed is the correct answer. So we reasoned it out and we confirmed it. So there's the first part. Draw the free body diagram on that charge. Find the speed of the ions going straight through. We did on the previous slide, we said V equals E over B. If this were a test question, you got to start from scratch. Sum of the forces equals 0 and find that expression for V, so that's the expectation there. So for the second part, we know the sum of the forces in the y direction is mass times acceleration in the y direction. FB minus FE equals m times 0. So here I'm just going in the y direction. I've dropped my vector notation. This one's positive because it points up. This one's negative because it points down. So this is kind of the more standard way to do it. So force magnetic is QVB sine theta minus our electric force QE equals 0. Sine theta is equal to 1 because theta is equal to 90 degrees. QVB equals QE. Divide through by Q, B equals E over B. Our electric field was 1 times 10 to the 6 newtons per coulomb. Magnetic field was 33.3 Teslas. So particles that are moving with a speed of 3 times 10 to the 4 meters per second are the ones that will go straight on through. And then the last part, we've got like 30 seconds left, so clearly I was too optimistic. Why don't you try this last part, see if you can get an answer, and then we'll just quickly go through that one at the beginning of Friday's class.